A Toon shader, like the ones you can see in games like Zelda Breath of the Wild or Genshin Impact, allows us to make our 3D scene look like it was taken out from a comic book or a 2D animated show. And the way it works is easy to understand, since all we need to do is take the lighting of our 3D scene, and instead of having smooth transitions between the parts that are lit and the ones that are in shadow, as you can see right here, we define a threshold for the amount of light an object in the scene receives, and make it so areas that exceed this threshold are considered as fully lit, and areas of the scene that do not receive this minimum amount of light are considered as in shadow. Okay, so here I'm in Unreal Engine 5, and the first thing I'm going to do is create a material in which we are going to implement the logic of our Toon shader. So I'm going to press Ctrl plus space on my keyboard to show the content browser, right click, select material, and then I'm going to rename it to pp_Toon shader for post-process Toon shader. I'm going to open it. And here, by default, a material allows us to modify the look of an object. Here, for example, if I press 3 on my keyboard and left-click in the graph, then connect this new node to the base color output and change its color, let's say a pink one, for example, this will change the color of the sphere in the viewport. However, what we want to do here is, instead of modifying the look of an object, we want to modify the look of what is shown on screen. In order to do this, we are going to change the type of material by going in the details panel right here. And then I'm going to change the material domain, which is available right here, material domain. I'm going to change it to post-process. So here, as you can see, the screen turns black, not pink, because now if you want to modify the look of the screen, we need to plug our color in the emissive color instead of base color. So here I'm going to click right here and drag a wire in the emissive color. And there you go, we have the look of our screen that was changed to a pink color. Okay, so now a pink color is great, but to apply our Toon shader, first we need to get the look of the scene as is and plug it in the emissive color. So I'm going to delete this constant tree node. I'm going to right-click, type scene texture, select the scene texture node right here. Then I'm going to select right here in the scene texture ID, I'm going to click and select post-process input 0, this one. Post-process input 0 represents the look of the scene without any effect applied on it. So here, if I'm going to plug the color in the emissive color right here, you can see that we created a pass-through post-process effect, which means that this changes nothing to what the screen is supposed to show. So here, just so you know how it's possible to modify the look of the scene, we are going to desaturate it to give it a black and white effect by dragging the scene texture node here. I'm going to drag a wire from the scene texture node and tap desaturation. I'm going to select the desaturation node, this one. If I plug the emissive color right here, you can see that everything turns gray. So now that we have a simple black and white effect, and before applying it to the scene, we're just going to change another parameter by going in the details panel right here. I'm going to search for blendable location. I think it's at the bottom of the details panel here. You have the blendable location. You are going to select this, and instead of taking the after tone mapping, we are going to check the before tone mapping option. So I won't go into details here, but just so you know, if we don't change this now, later, this will make the screen jiggle when we'll implement our Toon shader. Okay, that's great. So now that we have our base shader, we are going to go back to the viewport so that we can apply it to our scene. So first, we are going to create a material instance that will allow us to modify the parameters of the shader and see the result in the viewport without having to recompile the whole material. So I'm going to press Ctrl plus space on my keyboard. I'm going to right-click on the PP Toon shader, post-process Toon shader, and select Create a Material Instance. I'm going to rename it to PPI for post-process instance _ Toon shader. Then to apply this material instance to the scene, I'm going to go right here, click on it, select volumes, and then select post-process volume. I'm going to add this post-process volume to the scene. This will be right here. Okay, so I have my post-process volume. And then in the details panel on the right, I'm going to put myself in the middle of the screen. Here in the right, you have the details panel. You are going to search for post-process material. This is right here. Rendering features, post-process material. I'm going to unfold this. Press on the small plus sign. Then click on choose right here, asset reference. And then here, Unreal is going to ask me to select an asset. So I'm going to press PPI on my keyboard and select the PPI Toon shader. So here you might think that it doesn't work, but by default, a post-process volume applies the effect assigned to it only if you go within its bounds. So here, if I go in the bounds of the post-process volume, right here, you will see that everything becomes gray. So this means that the material was applied correctly. So to apply this effect to the entire scene, we need to check a parameter in the details panel, which is called infinite extent. So the infinite extent, it's right here below in the post-process volume settings. You have the infinite extent unbound. I'm going to check it. And voila. Now that we've finished the setup of our post-process material, we can start modifying it to apply our toon shading effect. Okay, so now that we know how to sample what is shown on screen, we are going to extract the light buffer from it so that we can access the amount of light each pixel of the screen receives and later perform some thresholding on it to create our toon shading effect. So here, to be able to extract the light buffer, first I'm going to get the base color of the scene without any lighting applied to it. I'm going to select the scene texture node, press Ctrl plus D on my keyboard, and here, instead of selecting the post-process input option, I'm going to select the base color as stored in gbuffer option. If I plug it in the emissive color output and then press apply, if I go back to the viewport, you will see that we have only the color information from the scene without any lighting applied to it. So here I'm going to get the desaturation node right here, press Ctrl plus D on my keyboard, and then plug this in to desaturate the base color of the scene. Now, what's cool about this is that if we divide the desaturated version of the scene by this, we're going to remove the color information from the render and only keep the lighting information. So here I'm going to drag a wire, type divide, and plug this in. So I'm going to divide the post-process input 0 desaturated by the base color desaturated. So finally, before plugging this to the output of the shader, first I'm going to add a saturate node to make sure that the values stay between 0 and 1. Then, since what we've created outputs an RGB color, and since the R, G, and B components of that color all have the same exact value, we are going to use a component mask node to extract only one of these components. So here on the left side of the screen, you have the components that are outputted by the component mask. And here I'm just going to select the red component. Okay, so now let's comment this bit of code. Let's say that we can extract the light buffer. I'm going to plug this in. And there you go. If I go back to the viewport, you will see that now we have the lighting information of our scene. Pixels that are white represent the pixels that are lit, and pixels that are gray or black represent pixels that are in shadow. Okay, so now that we have our light buffer, we are going to perform some thresholding on it so that areas of the scene that receive an amount of light that is greater than the threshold are considered as lit, and areas that receive an amount of light that is smaller than the threshold are considered as shadowed. So I'm going to go back to my shader, and contrary to what you might think, it's quite easy to achieve since all you need to do is add a step node to the graph like this. I'm going to right click here, type step. I'm going to select the step node right here. Then I'm going to plug this in the X input, this in the emissive color output of the material. Then on the Y input of the step node, I'm going to right click, select promote subparameter, and rename this parameter to light shadow threshold. I'm going to set its default value to 0.5. And here, by doing this, we tell Unreal Engine to return a value of 1, so a white color for pixels that receive an amount of light above this threshold, and a value of 0 for pixels that receive an amount of light equal to this threshold or below it. So 0 equals a black color. So that's great and all, but if I go in the viewport, you will see that the transition from black to white is a bit too hard. So now we are going to try to smoothen it a bit. So what we would like to do here is still use the light shadow threshold, but along with that, we are going to create another parameter called light shadow transition size. I'm going to select the light shadow threshold, press Ctrl+D on my keyboard to duplicate it. Then I'm going to rename it to light shadow transition size. Then I'm going to set its default value to 0.2. And here, this parameter will help us define, as its name suggests, the size of the transition. To be more precise about what we are trying to achieve here, if I set the threshold at 0.5 and the transition size at 0.2, this means that we want the transition to go from 0.4 to 0.6. And what we expect our shader to do is return 0 for pixels that receive an amount of light below 0.4, 1 for pixels that receive an amount of light above 0.6, and a smooth gradient going from 0 to 1 for pixels that are in the transition zone, in other words, for pixels that receive an amount of light between 0.4 and 0.6. And to achieve such a thing, we need to use a smooth step node instead of a step node. So here I'm going to right-click, type smooth step, this. And this node is exactly what we need, since the way this node works is as follows. First, it gets a value as an input, as well as a minimum and a maximum value, and then it returns 0 for values that are below the minimum, 1 for values that are above the maximum, and a smooth gradient for everything in between. Now I'm going to code something, and then I'll explain it to you how it works. So here, I'm going to delete the step node, then I'm going to get the light shadow transition size, multiply it by 0.5. Then I'm going to get the light shadow threshold, drag away from it, get a subtract node, plug the multiply in the B input, then drag another wire, type add, then plug the multiply node in this. And then I'm going to get the smooth step node, plug the result from the light buffer here. In the max, I'm going to plug the add, the subtract, I'm going to plug the min, and then I'm going to plug this in the emissive output of the material. Then I'm going to add a small comment. I'm going to type light shadow transition. Okay, so here what we've done is exactly what we wanted. We take the transition size, this one, divided by 2, and remove it from the threshold to get a value of 0.4 that we plug in the min input. Then we get the transition size divided by 2 and add it to the threshold to get a value of 0.6 that we plug in the max input. So now if I go in the viewport, you will see that we have a smooth transition from black to white. Of course, here, if you want, you can still go back to a hard transition by setting the light shadow transition size to 0. So if I save and go back to the viewport, you will see that the transition is hard again. Okay, so now you can see the code that we've created so far as the new lighting of our scene. However, I think that you'll agree with me when I say that a black color for areas that are in shadow and a white color for areas that are lit is a bit too harsh and not interesting at all. So to make this lighting more interesting, we are going to implement something that will allow us to tint the light and simulate, for example, a bluish lighting for when it's daytime and a slightly orange lighting for when it's the end of the day. So what's cool about the implementation that we've done is that since the value of the light amount is always between 0 and 1, all we have to do to achieve such a thing is to use a lerp node. So here I'm going to right-click, type lerp, and select linear interpolate, this one. Then I'm going to plug this in the alpha input, this in the emissive color, and here I'm going to press V on my keyboard and click in the graph to add a vector parameter that I'm going to rename to shadow tint. Then I'm going to select this, press Ctrl+D on my keyboard to duplicate it, and I'm going to rename it to light tint. The light tint, I'm going to plug it in the B input, the shadow tint in the A input. Then the shadow tint, I'm going to select this, change its color to, let's say, something like a gray color, put an alpha of 1 here, And the light tint, I'm going to double click on it and select, let's say, a white color. Alpha at 1, press OK. And here, by doing this, we tell Unreal Engine that if the value from the smooth step is equal to 0, in other words, when a pixel is in a shadowed area, instead of setting its color to black, we change it to the color defined by the shadow tint parameter. On the other hand, if a pixel is in a lit area, instead of returning a white color, our shader will now return the color defined by the light tint parameter. And last but not least, for all the pixels that have a value different from 0 and from 1, the lerp node will blend the shadow tint and light tint based on the amount of light they receive. So for example, the color of a pixel that has a value of 0.3 will tend to be more like the shadow tint than the light tint, and the color of a pixel that has a value of 0.5 will be a perfect blend between the shadow tint and the light tint. So now things are starting to get really interesting, and if you go in the viewport and open the material instance, press Ctrl plus space, open the PPI Toon shader, here you can change the parameters, the light tint and the shadow tint. You can set them to interesting shadow and color tints to get a cool result. However, based on what you need to achieve, you might think that we have a small problem with the shader. Okay, so here it's a bit subtle, but if you try to move the camera around, maybe you'll find some weird artifacts appearing like inconsistent shadows, like you can see right here. So I've investigated this issue and found out that it was due to Lumen, the global illumination solution of Unreal Engine 5. Since Lumen calculates reflections and global illumination in screen space, I think that this causes inconsistency in the lighting. And to fix this, all you have to do is deactivate Lumen by going in the project settings, so Edit, Project Settings right here. Then you go in Engine, this, and search for Rendering. And here, if you go down, you will see that you have Global Illumination and Reflections set to Lumen. You can select this and set it to None, select the reflection method and set it to None instead of Lumen. And if you save it and go back to the viewport, you will see that there's no more artifacts going on in the scene. So of course, doing this will remove the global illumination in your project. So you need to make sure that you don't need it before deactivating Lumen. And just so you know, later in this video, I'll show you how to apply the effect only on some actors of the scene. So if you plan to apply this shader only on your characters, like in the game Genshin Impact, for example, then you can turn on Lumen, since it doesn't seem to create these artifacts on skeletal mesh, like the characters, for example. So as for me, I don't mind these inconsistencies in the lighting, so I leave Lumen turned on. Okay, so now that the new lighting of our scene is set up, we need to apply it to the scene. So applying a lighting to a scene is as simple as blending its color with the base color of objects by multiplying them together. So here we are going to get the scene texture node we used earlier to get the base color of the scene without any lighting applied to it. So I'm going to get this one, the scene texture base color. I'm going to press Ctrl D on my keyboard to duplicate it, bring it right here. Then I'm going to multiply this by what we've created so far. So here I'm going to drag a wire from here, multiply, plug it right here, and this right there. So here Unreal Engine is giving us an error right here. Because the colors from the light and shadow tint parameters are composed of three components, red, green, and blue, whereas the one from the scene texture node is composed of those three components, along with an alpha component that represents the opacity of the color. So to solve this error, all we need to do is remove the alpha component from the color of the scene texture node with the component mask node that we've used earlier. So here I'm going to drag a wire from this, type component mask. I'm going to plug this in the B input, and here I'm going to check the R, G, and B component so that we have three components in the color from the scene texture node. So here, if I save it and go in the viewport, you will see that the shader seems to work correctly. However, there's a problem with the way it works. Here, if I place, for example, a point light, I'm going to go right here, select lights, and place a point light in the scene. This way, for example, I have my point light right here. the lighting information is taken into account, but if I change the light's color to something like a pink color, you will see right here that the lighting color doesn't change. Okay, so to solve this issue, we are going to use a little trick that will allow us to add to this result the original color that the scene had before we applied our Toon shader on it. So here I'm going to put myself on the right side of the screen. I'm going to go back to my Toon shader. And here what I'm going to do is that I'm going to duplicate the scene texture node right here, Ctrl+D. I'm going to select the post-process input 0 to get the color of the scene without any effect applied on it. Then I'm going to multiply, to add a multiply node. I'm going to right-click on the B input, select promote to parameter. I'm going to rename this new parameter to base render blend amount. I'm going to set its default value to 0.5. And then I'm going to add this to this, okay? By doing this, I'm going to add the color from the scene before the Toon shader is applied on the Toon shader. So here, the base render blend amount allows us to define how much we want the original color of the scene to be added on top of the shader. If you don't want any color from it, you can set the base render blend amount to 0. And if you want all the information from the base render, you can set its value to 1. So here, if I save and go back to the viewport, you can see that we have our pink lighting that appears on the rendering. Okay, so now that we have our base Toon shader, now we are going to make it so the effect is not applied to things that are too far away from the camera, like the sky, for example. So first of all, we are going to create a parameter in the Toon shader that will help us define the maximum distance at which the Toon shading is applied. So here I'm going to right-click, type scalar parameter. I'm going to rename it to effect max distance. And I'm going to set its default value to a really big value, like let's say, for example, 500,000. It's over 500,000. Okay, then we are going to get the scene depth node that will allow us to get the depth of each pixel of the screen, and we are going to compare its value with the parameters by using a step node. I'm going to plug the scene depth in the X, and the effect max distance in the Y input. So here, for each pixel that is farther than the effect max distance, the step node will return 1, and for pixels that are closer than the effect max distance, the step node will return 0. Now, all we need to do is tell Unreal Engine that we want to apply the shader on pixels for which the step node returns a value of 0, and not apply the shader on those for which the step node returns a value of 1. So to do something like this, I'm going to add a lerp node. I'm going to right-click, type linear interpolate, and just so you know, I can press L on my keyboard and left-click in the graph to add a lerp node. So here I'm going to plug the step in the alpha. Then I'm going to plug the result of my Toon shader in the A input. And here in the B input, I'm going to get the scene texture post-process input 0. I'm going to duplicate it to get the rendering from the scene without any effect applied on it. Then I'm going to drag a component mask, select R, G, and B, and plug this in the B input. Okay? By doing this, we say that if a pixel is closer than the max distance, we get the Toon shader, and if the pixel is farther than max distance, we get the rendering of the scene without any effect applied on it. So here, if I save it and go in the viewport, you will see that the skybox is not affected at all. So to better show you the result, I'm going to open the PPI Toon shader, and let's say that I add a bluish color to the lighting, or yellowish color, this for example, and a pink color for the rest. You will see that the sky is not affected by the effect. Okay, so now we are going to add the ability to apply our Toon shader only on some of the actors of the scene. This can be useful, for example, if, just like in the game Genshin Impact, you want to apply the effect only on the characters and leave the environment as is without any Toon shading applied on it. to be able to do something like this, we are going to use the custom depth buffer. And for those of you who don't know what the custom depth buffer is, you can see it as an additional depth buffer in which you can choose what actors of the scene you want to sample. And to better understand how it works, if I go here in the lit, select buffer visualization and show the custom depth, you will see that the screen becomes completely black since nothing was added to the custom depth buffer. If you want to add an actor to the custom depth buffer, you just have to select it in the viewport, and here in the details panel, you're going to search for custom and check the render custom depth path option. As soon as you do it, you will see that the selected actor becomes gray, which means that it has successfully been added to the custom depth buffer. Okay, so now to make it work, I'm going to check if an actor is in the custom depth buffer or not in my Toon shader. So here I'm going to go back to lit mode, then in my Toon shader, I'm going to grab the code for the Skybox and put it over here. Then here I'm going to right click, type scene texture, select the scene texture node, and here in the scene texture ID, I'm going to select the custom depth option. Then I'm going to drag a wire, type component mask, and select the red channel only. So by doing this, I'm sampling the custom depth. And when I sample the custom depth buffer, it will return the depth of a pixel if it's present in the custom depth buffer. And if this pixel is not in the custom depth buffer, it will return a depth that is really big, like 100,000, for example. So now that we have this information, we can compare what comes out of these nodes with a really big value. Let's say I'm going to right click, type step. I'm going to get the step node. Here, I'm going to press 1 on my keyboard and click. I'm going to plug it right here. Okay, so just so you know, this is a constant. Right click, type constant and select constant. This is just a value. You can select this constant and put it to a really big value. Let's say, for example, 500,000, for example, here. And by doing this, if the custom depth buffer returns a really big value, in other words, if the pixel that is sampled is not in the custom depth buffer, the step node will return 1. Here, to make it work with the code I'm going to create later, I'm going to inverse this result with a 1 minus node. Here, I'm going to drag a wire, type 1 minus. And so by doing this, if the pixel is in the custom depth buffer, it will return 1, and if it's not, it will return 0. So now, just like we did when we isolated the sky from the effect, we are going to use a lerp node. So I'm going to go to the sky code, like here, right this. I'm going to select this part of the Skybox isolation code. I'm going to press Ctrl plus D on my keyboard. And here, I'm going to get this. I'm going to plug the multiply node right here in the B. Post-process input 0, I'm going to plug it in the A input. The scene texture custom depth, I'm going to plug it in the alpha. And this, I'm going to plug it in the other lerp node. Okay? So now what I've done here is that if this code returns 1, which means that the object is in the custom depth buffer, then we are going to apply our Toon shader. If not, we are going to show the color of the scene without any effect applied on it. So here, if I go in the viewport, you will see that the effect is applied only on this actor. Okay, if I select this one and select the static mesh, then custom depth, you can see that this is applied on the object. However, if I go underneath the platform, you will see that we can see that the actors are shown even when we place them behind other objects. So now I'm going to go back to my shader, and to solve this issue, we are going to add some nodes to the graph, and then I'm going to explain to you how they work. So here, I'm going to get this part. I'm going to right-click, type scene depth. Then from the scene depth, I'm going to get the component mask, duplicate it, plug it right here. Then I'm going to get the scene depth, drag a subtract node, and plug the custom depth in the B input. And then I'm going to get a step node right here. I'm going to plug the subtract in the X input, remove the connection to the Y input. Then I'm going to multiply this by this. And then I'm going to plug this in the lerp node. So what this code does is it checks if the depth of a pixel is equal to what is stored in the custom depth. If it is, then this means that not only is the pixel in the custom depth buffer, but it's also the closest one to the camera, and it's not obstructed by another object. So we make sure that the object is in the custom depth buffer and that it is in front of the camera. So now, before going in the viewport to check if it works, we are just going to add a node that will allow us to activate or deactivate this feature. So here I'm going to drag a wire, type switch parameter, and then I'm going to select the static switch parameter. Here I'm going to rename it to custom depth buffer. Then I'm going to double click on this wire to create a reroute node, plug it in the false output, and then plug this right here. Okay? So if the custom depth buffer switch parameter is equal to true, this will activate the custom depth buffer feature. And if it's false, this will deactivate the custom depth buffer feature. So now I just have to apply it, save it, and if I go to the viewport, you will see that our Toon shader works correctly, so that's great. And now if you want to upgrade this Toon shader like this by adding outlines to the actors of the scene, you can have a look at this video and I'll see you over there to make our greater than this threshold where it's too far away. This by